All right, welcome back to our videos for Unit 6 of the Game Engines class. And in this unit, what I'm going to do is to create a mesh in the scene, and it's going to be our Sinbad mesh. And we're going to place it on the plane with the beach stones on it applied as materials. And then we are going to use our directional light to create shadows on the scene. So the first thing that we need to do is to create an entity for our Sinbad mesh. So we're going to create the entity pointer for the Sinbad, and it's going to be from the mScene manager, create entity, and I'm going to call this Sinbad, and actually let's make it Sinbad01. You may have multiple of these entities, and we're going to bring in the Sinbad mesh from our media. Then we're going to create a scene node for the Sinbad. I'm going to call it, we are going to call this Sinbad node, and it's going to be a child of let's actually see, what do I want to do with this? I want this node to be actually a child of the root, so that I can independently move this mesh around, or this node around. So let's actually remember, did we have a root scene node? No, we didn't really create a node to represent the root scene node. So what we are going to do is we're going to create this as the, let's just go ahead and create a scene node and call it Sinbad SC node. And then add the scene node as a child of the root. So this should create the Sinbad node that is independent of where our lights are. And that's what makes perfect sense for me at this point to do. Then we're going to go and scale the Sinbad node to about 5. And then attach the Sinbad entity to it. Now, if I run this code, the Sinbad should kind of be placed at the kind of like on top of the plane, but I guess probably from about the waist down it's going to be buried. And that is because the scene node is now kind of at 0.0.0, so we need to move it about a little bit. But now we're going to compile this code and run it and see what happens. Okay, so as you see, as I mentioned, the Sinbad node is basically, or rather the Sinbad mesh, the pivot of the mesh is at the waist and at the pelvis of the mesh, and so we need to move the node upwards so that its feet would be on the ground. So let's do that. So then we're going to go and do a translate on the Sinbad node. and we're going to translate it for about, I guess, about 40 units upwards on the y-axis. Oh, 40 units was way too much. You know what I'm thinking? Let's scale the Sinbad up. Yeah, let's set the scale instead of 5 to something like 10. And now the Sinbad's feet seem to be pretty much on the ground. And obviously, as you see, the light direction is pretty much from the kind of diagonally going from the upper left corner and shining down to the lower right corner of the scene. So this is looking pretty good. However, the problem that is missing, the Sinbad itself, as you see, the light is reflecting shadow on it. So the mesh of the Sinbad is already created in such a way that it does create shadows. However, on my plane, there are no shadows created when the light is actually shining on the object. So what I need to do is to go ahead and enable these shadows, or rather add shadows to my scene. It's actually fairly straightforward. Just one line of code will take care of the shadows for me. So what I need to do is to go into the scene manager and then set the shadow technique. And there is only one parameter that goes into the shadow technique, and that is just the shadow type. So my shadow type, if you type in shadow type, you will notice that there are 7 different shadow types. You can have shadow type none, which is the default shadow technique. You could have shadow type stencil or shadow type texture. 2 shadow type stencil and 4 shadow type textures. So shadow type stencil could be either additive or modulative. Effectively, in the additive mode, when you have multiple objects, shadows are going to be added on top of each other. In terms of modulo, there's going to be a little bit more complicated computation that goes into it. And with texture, you can also have additive and modulative. And for each of those, you can also have integrated versions with them. So the shadow type texture modulative is the least computationally extensive of these kinds. Basically, what's going to happen is that a black and white render to texture is created that will be using all of the shadow casters in the scene, all of the objects that are enabled to cast shadows, and then this will be applied to the scene. In terms of your stencil shadow types, the shadow type stencil modulative basically renders all of the shadow volumes as a modulation after all of the non-transparent objects have been rendered onto your scene, and then the shadow will be applied. And it's not going to be it's kind of like a reasonable and nice calculation. Shadow stencil additive, though, it basically creates the same kind of concepts with your textures, and it effectively creates each, or rather renders each light as a separate additive pass onto the scene. So if you look at the complexity of your calculations, your shadow textures are going to be the least complicated. Shadow stencils are going to be the more complicated, and among the two, shadow stencil modulative is going to be the least complicated of all. But shadow stencil additive is effectively the one that is going to be quite resource intensive, because it basically uses each light as an independent computational model, and then calculates the shadows off of that each light, and then adds all of those together to create the result of your entire shadow calculation. So what we're going to do here is we're going to use shadow stencil additive. Since we only have one light in the scene, it wouldn't really cause computational complexity for us and speed us down. We only have one light. So we're going to compile this code and see what happens. And when we go up, you would see how your shadows are now calculated. So we have a shadow for the Sinbad, and as you see, the shadow is pretty strict, and is when it's calculated and added to the scene. Now let's make the shadow to be modulative. Compile and run. And as you see, the modulative shadows are a little bit more accurate in that they are effectively applied on top of the actual surface light computations, and so your shadow is just not a black and white stencil. Now, to show you the effects of using the shadow stencils with multiple light sources, we will go in and uncomment all of our lights and then compile and run the code. And as you see here, we have multiple lights that are affecting our scene, and with the shadow stencil, you will be able to see that we have now multiple shadows, effectively casting object shadows and light shadows on our scene. And finally, let's try the additive mode. Compile and run. And obviously, as you see, the shadow modulative, or rather the shadow additive, is just a little bit more accurate. And especially when you have multiple lights in your scene, the representations that you have are going to be a little bit more clear. I'm not going to go into any details about how these shadows are calculated. There are a large number of different resources out there that you can look at. So this is how you can actually create shadows in your scene. Effectively, a simple line of code that kind of toggles and enables your shadow, and also chooses the type of shadow that you want to implement. All right. One of the things that we have noticed so far is that when we run our application, the camera is kind of on the ground plane, and it doesn't really look nice. I mean, every time I run the program, I have to move in and actually kind of make the camera move upwards and then look down to see my scene. It's because the camera that we have established, or rather we haven't established at all. So the system, the base application that we're using, it basically uses the already created camera from the application, example application that our application inherited from. So the application actually has a camera already created, and the camera is positioned at the 000 location. So that's why this camera is kind of like placed at the ground level, and every time I run, I have to kind of make it go upwards and then kind of get a good view of the scene. So now what we're going to do is we are going to go and create a camera. To create a camera, the process is actually fairly straightforward. Same as creating a scene. As you see here, we overrode the create scene method of the example application, and then in the create scene is where we actually place all of our scene nodes and effectively our scene graph representation. The Ogre applications also utilize a create camera method. So in order for us to be able to create this camera, we will actually have to override it. So we're going to go and create a create camera function. And then we are going to go and create a member variable for our application, or rather set it up. So this member variable is called mCamera. And we are going to create from the mScene manager create a camera. And I'm going to call this my camera 01. Just similar to the camera that like the lights that we created, we will be able to set the position of this camera and its other parameters. So the parameters that we have is the position. One of the parameters is the position. So you're going to set the position of this camera. And for now, let's make it 0 and 100, and let's say 200. And another property that this camera has is called the look at. So we would set the mCamera look at property and make this to look at our origin of our scene. There are two other properties that our camera possesses: a near clipping plane and a far clipping plane. And we're going to set these two up as well. Set near clipping distance, and we will set this as 5. And then we'll compile and run our application. And as you notice now, our camera is kind of placed at a higher angle. So we have a better view of the scene. Let's actually go ahead and make it a little bit further out. Remember, X is the axis that points to the right, Y is the axis that points upwards, and then Z is the axis that points outside of the monitor. And so we effectively make our camera to go up about 100 units, and then 400 units out of the monitor. And so as you see, that's where the camera is located. So creating a camera is actually fairly straightforward and relatively accessible. One of the nice features that the camera has, when we create a camera and place it in the mCamera member variable of the base application, or rather the example application class, we will be able to actually use this mCamera as an object and attach it to scene nodes, create scene nodes for it, and place it in a scene node. And so we'll be able to actually manipulate and control this camera. So what I'm going to do is, right now what we have created is in the mCamera, in the create cameras function, we set the position of the camera and its look at, so that we'll be able to actually for the camera to be able to see and look from the front view of the scene. What I'm going to do now is, let's go and we are going to actually cancel the position and the look at, or rather comment out the position and the look at of our mCamera. We already created the mCamera with the scene manager create camera method. And now what I'm going to do is I'm going to go to the set scene or create scene, and from there I'm going to create a scene node for this camera, attach the scene node to the Sinbad node as a child, and then move it out, and then place the camera in it, and then rotate the camera and set its look at, so that it is kind of like a third-person camera view. So we're going to go and create a scene node pointer, and let's call it camera node. M scene manager create scene node and call it camera node underscore 01. Then we are going to attach the camera to this node. So camera node attach object mCamera. This attaches the mCamera that we created in the create camera method into this scene node. What I'm going to do then is going to use this Sinbad node and add the camera node as a child to the Sinbad node. So now I have my Sinbad node, and then the camera node is also attached to it. However, I want this camera node to go behind the Sinbad node, so we will make the camera node to translate zero units on the x-axis, 10 units on the y-axis, and then let's say negative 20 units on the z-axis. This will make my camera to be placed behind the Sinbad node. Then we are going to also turn the camera around, and since I want the camera to be turned around on its y-axis, I'm going to use the yaw method. So camera node yaw, and I want it to go 180 degrees. And then set the mCamera and look at 0, 0, 1, 0, which is basically the center of the scene. Well, actually, let's make it to go look at 0, 40, and 0. And let's compile and run this project. And this is how now my camera looks like from behind the Sinbad. Let's make this camera to go a little bit farther out on its z-axis, and on its z-axis. Let's make it to go negative 50. Compile and run. Okay, this is actually pretty nice view. Maybe 50 was too much. We'll make it 40. All right, this is now a relatively nice third-person camera that is set up to look over the shoulder of the Sinbad. Now, if we were to move the Sinbad about in a game, since our camera node is attached to it, the camera will follow the Sinbad. However, right now our controls are done through the base application, so we still will be able to move the camera, but not the Ninja, or rather the Sinbad, independently. So now our camera is set up. And one last thing before I wrap up this video is to set up a viewport for our rendering. And just like the create camera function and method that we utilized, we can actually go ahead and override our create viewport. And that's what we are going to do now. So we go and create our viewports function to override, and then we will create a viewport pointer. Let's call this VP. And the viewport basically gets the M window member variable of our example application and adds a viewport by passing into it our camera. So to establish this, we are going to call the mWindow member variable and then add viewport to it based on mCamera. let's obviously it should be viewport, not viewport. Now next we are going to go and set the background color of our viewport to a color value of let's make it a relatively bright gray, so 0.9 F, 0.9 F, and 0.9 F. And then we are going to set the aspect ratio of our camera to the aspect ratio of the width and height of our window, or rather our viewport. So M camera, set aspect ratio. And in the aspect ratio, we effectively require to pass a real value, and this real value is going to be the width of our viewport over the height of our viewport. So VP get actual width divided by VP get actual height. Now let's compile and run the application. Let me actually make this real of viewport height, real of viewport width, and then 0.9 was probably too much, so we're going to do 0.75. 0.75 for the background. It's going to be a little darker gray color in the background of our viewport, and the aspect ratio. Okay, this looks much nicer. The problem previously was the viewport got squished a little bit, and the problem was when I was setting the aspect ratio. If you remember, I used the viewport get actual width divided by get actual height, and these values may be integer values, and it might result in integer division, which basically gives you a wrong aspect ratio. So what I did is actually I passed get viewport actual width, and I passed it into a function called real. Let's actually go and look at it. So here I did get actual width, and then I passed it into a function called real. So this function basically takes the actual width and then returns a floating point value, and same thing with the real of get actual height, so that your aspect ratio would be actually properly set up. So what I want to do now is also to go and change the aspect ratio of the width and height, as you see. So let's go and change your width and height. And so the viewport, when you change it, when you change your window, your aspect ratio actually changes also accordingly for your camera, and it's set up properly. Okay, you maximize the screen, and so your viewport actually automatically gets updated. All right, so this is all I have for this unit. In this unit, we basically went ahead and learned about light, learn about how we can create meshes, and use the resource manager to create planes. We learn about different kinds of lights, spotlights, point lights, and directional lights. We learn about shadows in Ogre, and also we learn about how to set up a camera and how to set up a viewport for our applications. So we are actually getting really a lot of good information about how to set up our applications in Ogre, and hopefully this is going to be helpful for your future endeavors in developing games and even probably building your own engines from 3D software development kits such as Ogre. What is left actually of our journey with Ogre is to learn about user inputs and how we can utilize frame listeners to be able to read the keyboard inputs and the mouse inputs to be able to make our applications interactive. So far, as much as you have seen, the only interactions that we have designed and have had was through the use of WASD keys and moving around in the scene, moving practically the camera around. So we didn't have the ability to move the objects in the scene and to interact with them. So we're going to use that next, and then we will learn about animation and how Ogre utilizes animations, basically. So those are the two things that are left before we finish up our journey with the Ogre. Now, this is it for Unit 6. I let you go and study what you have learned in this project, and I will talk to you in Unit 7, where we will be able to utilize user inputs and create more interactive applications.